Hello everyone, welcome to the tutorial of heat source term modeling in Fluent. In this tutorial, we will simulate a fluid domain containing a heat source with laminar flow. The air is flowing with 0.01 meter per second over the heat source of constant rate 40,000 watt per meter cube, which results in convective heat transfer between the heat source and the air. The operating conditions of the flow is at standard pressure, which is 101,300 Pascal and 290 Kelvin temperature. The laminar viscous model is used to model the flow in ANSYS Fluent 2019 version R2. These are the dimensions which are mentioned on the screen, as well as the flow with velocity and temperature. So first we will begin with the geometry in Design Modeler and use extrude and blend tools to draw these cylindrical bodies which are over the hot plate. Then we will draw the domain and extrude it over the heat source. After that we will generate a mesh with body and edge sizing. Then we will check the skewness and orthogonal quality of the mesh. So first of all, we have to open this workbench program. Then we can select the geometry from component systems, and then we can select this mesh. After that, when meshing is performed, we can overlap it with Fluent setup, and then drop the results, or select the whole Fluent package for fluid flow. So open the geometry in new Design Modeler, select coordinate system. I will select ZX plane to draw the rectangular plate. Go to sketching, select rectangle and select the origin, but first of all select units to millimeter. So rectangle, and then this rectangle is generated but without specific dimensions. So use semi-automatic in dimensions list and set the dimensions. So the length along X plane is 50 millimeter, whereas the length along Z axis is 100. So after drawing rectangle with specific dimensions, use extrude with 2 millimeter depth and generate to obtain the rectangular plate. Now to draw cylindrical bodies over this rectangular plate, click Face tool and right mouse click to look at. Now go to sketching, click circle and draw two circles with some distance. Go to dimension, click semi-automatic and Set the dimensions. So the diameter of these two circles are the same, which is 25 millimeter, whereas the distance from the center to the axis of first circle is 25, while for second circle is 25 millimeter and 75 millimeter. Now use the extrude tool with depth 10 millimeter to obtain the cylindrical bodies. After that, go to blend and click fix radius by selecting the edges on the plate which are connected with this cylinder, and set 3 millimeter radius. Click apply and generate. Here we get the geometry of the heat source. Now we have to make the geometry of the fluid domain. In order to do that, navigate to XY plane and click to form the rectangle. Go to dimensions to specify the length and breadth. So the height of the domain is 40 millimeters and the length along x-axis, which is L2, is 130 millimeter, whereas the distance from the plate to the domain is 50 plus 40. So the concept here is to keep this plate at the center of the domain. Now use the extrude command, add frozen so that we can make two bodies, direction both asymmetric, so we will have both dimensions forward and backward. In the forward direction, the depth is 150 and backward 50 millimeters. So it is at the center now with distance of 50 millimeter along z-axis, and along x-axis it is with 40 millimeter distance. Click generate. Now we have to separate the domain from heat source. Click Boolean and operation subtract, target body, domain, tool body, heat source, and preserve tool body, then generate. So if we check by hiding the heat source, the domain is subtracted now. Now we can name these bodies by selecting the body selection tool and click name selected. Name it as fluid domain then select this heat source and name it as heat source. Now select the face tool and name it as well. This is the top wall. This is inlet. The back side is outlet. This is and this is side wall. This is the bottom wall. Now hide the heat source and also select the faces of connecting surfaces. All done. Now select these two bodies and right mouse click, form new part. All done. Now close this program and return back to Workbench. You should see a green tick next to the geometry option within your project. Now double click Mesh Program. I will use sizing for this mesh, but first I will select heat source, so hide the fluid domain. In sizing, select the geometry with body selection tool and set the element size of 1 millimeter. If the unit is in meter, set it into millimeter. So 1 millimeter element size. Now I will also insert sizing for the edges of the cylindrical bodies. Select the edge tool and hold the control button to select the edges. Use number of divisions. I will select 100. Now for the body sizing of the fluid domain, show body and insert sizing, selecting the fluid domain. Here first check element size of 4 mm. Right mouse click mesh and generate mesh. So the mesh is generated. We can check the quality by using display style as orthogonal quality. Orthogonal quality or orthogonality of the mesh is comparative measurement of closeness of the angles between adjacent element edges or faces to the optimum angle. So it ranges from 0 to 1. 0 is bad and 1 is good. So most of the area is near to 1. So orthogonality is good of this mesh. Now check skewness. Let's see what is behind this heat source. So for the flat surface, the skewness should be close to 0. Close to 0 is a good value and close to 1 is bad for skewness. Let's see. If I set the element size of heat source to 2 mm, so the skewness is also good here. Most of the area is blue in color, which means the minimum value of skewness. So now close the meshing program. Now double click setup, double precision for more accuracy, and parallel for multi-core processors. I have 4 logical processors. So in general setup, retain default values for all parameters, but check and set Y value to minus 9.81. By clicking report quality, you can check the maximum aspect ratio and the orthogonal quality as well. So it should be positive so that the mesh is not distorted. On the left hand side, click models and double click the energy to set the energy equation, because there is heat transfer occurring in the system. Retain default settings for all, because the flow is laminar, so the viscous model to be laminar. Click cell zone conditions and select heat source. Click source terms and set source term to 1 number of energy source. Click constant and set the value to 40,000 watt per meter cube. Now click boundary condition and double click bottom wall. Go to thermal tab and select via system coupling. Similarly for connection wall, check if it is coupled, then OK. Side walls, via system coupling as well. Top wall, now select inlet and set magnitude of velocity to 0.001 in the momentum tab, and in the temperature 290 Kelvin. For outlet, set type to outflow. Retaining all the parameters as default. Now click methods and select Simplec. This Simplec is simple consistent algorithm, which is a modified form of simple algorithm in computational fluid dynamics, and it is used for velocity pressure coupling. It allows faster convergence for simple equations. So set the gradient as green Gauss cell based. And with all second order upwind schemes for momentum and energy. Retain all the default values for all parameters in solution controls and in monitor residuals. Set all the residuals to 1 exponent minus 6. This will converge all the values with the residuals of 1 exponent minus 6. Go to initialization and select standard initialization with compute from all zones and click initialize. So initialization is done. Now click run calculation and set number of iteration to 1000 and click calculate. So I will pause the recording here and wait for the solution to complete. The solution was interrupted around 350 iterations, so I have to run 1000 iterations again, and the solution is completed at 1200 iterations, but it is not converged yet. So I will check the results now. So close the Fluent and return to the workbench program. You should see the green tick next to the solution, and now double click results. So far we have completed pre-processing, in which geometry and mesh is completed, then processing, in which setup and solution is performed. Now in post-processing, CFD post is used, in which we can generate vector plots, contour, streamline, and particle track, and many more. We can also generate charts in this to check the variation of temperature, velocity, and many different variables. So let's see temperature contours. So click contour, insert contour. Let's see what is the temperature variation at connection wall. So select variable as temperature, number of contours 100, and apply. So this is the heat source, so obviously the temperature is high. We can set scientific notation into fixed in default legend view. Also we can size the parameter. Now similarly, another contour, we can check the bottom wall with 100 number of contours of temperature. So we can see the color map, how temperature is varying. The variation is shown here. At inlet, temperature is initially 290 Kelvin, and then along the axis of domain, the temperature increases when it flows over the wall. We can save the plot by using this icon. Click white background, and we can change format to JPEG, image quality 100, and select the directory to save the image file. So this is the variation in temperature at the bottom face. Now if we want to have temperature contour variation in y direction, let's make a plane that section this fluid domain. Click location, go to plane, insert plane, and select YZ to slice the domain, and here set X value to 0.025 meters. We can also select millimeter. So if you know that distance from the center to the edge of the plate is 25 millimeter, because the width of the plate is 50 millimeter, so half of the value is 25. So select apply. So now you can see the plane is sectioning the heat source. Another contour of temperature. Now at plane 1, hide the previous contours. We can see the contour of temperature varying in y direction along the domain. Also we can generate velocity contour to check the velocity field distribution in this plane. So select velocity and plane 1 with 100 contours. So this is the velocity contour. We can see how the flow is moving across the domain. Okay, if you want to generate a horizontal sectioning plane, so we can add a plane in ZX directions. So if we set the value of y to 0, it will be at the bottom. let's see how it slices the domain at y equals to 10 millimeter. So we can set different planes, or with this plane varying the value of y, we can have different contours at different height. So let's see another contour of temperature. Now at plane 2, we can press Ctrl and roll the middle mouse wheel. So this is the inlet and this is the outlet. Now if we change the value of y in plane 2, we can see the variation of temperature field at different height. We can also check how the flow is moving across the domain by checking the 3D streamline plot. So click Streamline, insert Streamline and start from inlet with around 100 number of points, sampling equally spaced, and in all domain we will check the velocity. So this is a 3D streamline plot. We can also see surface streamline on the plane for plane 1, or we can check on plane 2. Changing the value of y. In order to check how the temperature is varying against the length of domain with different vertical distances, y equals to 5 millimeter, y equals to 10 millimeter, y equals to 15, 20, 30. So let's select the line tool, hide this streamline plot. Now we will insert a line at the middle of this domain, but with a specific height y. So insert a line y 2.5. so we have to make a line at the middle of the domain with a height 2.5 millimeter. So the point 1 will have coordinate of 0.025, which is 25 millimeter. No changing in x coordinate. Also 0.0025 and 0.0025, no changing in y coordinate. So this y coordinate is also set at 2.5 millimeter, not changing. But z coordinate starts from minus 0.05 and ends to 0.15. If you check the domain, we took some backward distance which is of 50 millimeter, so that is why it is negative, and some forward distance in z direction, that is of 150 millimeter. So set 50 samples and apply. we can set the color of this line, make it a bit darker. Similarly, we can duplicate this to make a line of 5 mm. Just changing the value of y. Duplicate this as well for 10 mm. Duplicate this for 15 mm. Duplicate this for 20 mm. And last of y equals to 30 mm. Now we can select chart and set the title of temperature variation. At the middle, now select different values of data set. So y2 space 5 is for 2.5 mm. We can select another series which is of 5 mm. So location is the second line. Similarly, now on x-axis select Z, and on y-axis select temperature. So that's all for today. Thank you for listening. In this tutorial, we have studied how to make the geometry, then how to perform meshing. After that, we studied how to set up and perform the solution. Finally, for the results, we studied how to perform post-processing in CFD Post.